On your own 4.1, an airplane flies with a velocity of 214 miles per hour at a heading of 65 degrees, including the effects of the wind. The pilot stays on that course for 2.10 hours and then turns his plane so that it flies with the velocity of 187 miles per hour at a heading of 335 degrees, including the effects of the wind. If the airplane flies on that course for an additional 1.40 hours, what is the plane's final displacement? Okay, the first thing to do here is to have a picture of what's going on. So let's look at the first part of the journey and try to get some of that drawn. Okay, so we need to have, let's line this up as good as we can. It does not need to be perfect. This is just to have a graphical representation of what's happening. So an angle of 65 degrees is right around here with a velocity of 214 miles per hour. So let's go ahead and draw that. Here we go. So this is the first leg of the journey. Let's figure out the second leg of the journey. We did our second parallel axis at the end of the first vector. And then we have to figure out 335 degrees from that. So this is 90, 90, 180, and 90 is 270 plus 65, 10, 20, 30, 40, 50, 65. So we're going to say that's like right around here. So then we have to just draw a vector that would represent that. Perfect. Let's just go over what it is we're trying to find now. This is the vector we're trying to solve for right here. This one in green. I will put this hash line here. This is what we're desperately trying to figure out. That vector. As with all such problems, we need to look for the one-dimensional situations within these two-dimensional problems. Each leg of the journey is an independent one-dimensional problem because the airplane travels in a straight line in each case. In the first leg of the journey, the velocity is 2.14 miles per hour. The acceleration is 0 because the velocity is constant. So let's write that down. Velocity equals 214 miles per hour. Again, the acceleration is 0 because the velocity is constant. The time is 2.10 hours. So then we have to figure out which of our one-dimensional equations we are going to want to use. Once again, we're going to use the one that solves for displacement. So we have delta x equals the velocity times the time plus 1/2 a t squared. Sometimes I just go ahead and get rid of this and turn this 0 because we know anything times 0 is 0. So now we're left with the displacement delta x equals 214 miles per hour times 2.10 hours. The hours cancel out and we're left with, let's grab our calculator and say 214 times 2.1 equals 449.4 miles. We know that's way too many significant figures because we can only have 3. So I'll mark it like I always do with my yellow star. And then our displacement for this is going to be 449 miles. All right, so is this our answer? Absolutely not. This was only the first leg of the journey. We did learn something though. We learned that the first leg of the journey resulted in a displacement of 449 miles at an angle of 65 degrees. That then is where the second leg of the journey begins. If we can figure out the displacement that results from the second leg, we should have enough information to determine the final displacement of the airplane. So once again, the velocity of the second leg is 187 miles per hour. 187 miles per hour. Velocity is constant, so we know that there is no acceleration. And the time, it says here, is 1.40 hours. So we have to figure out which of our one-dimensional equations we're going to use. We're going to use the same one. I'm writing that one now. And then once again, for this little portion over here, I'm just going to get rid of it, because with a zero acceleration, anything times 0 is 0. So we're left with the displacement is the 187 miles per hour times 1.40 hours. The hours drop out. And let's go ahead and grab the calculator and say 187 times 1.40 equals 261.8 miles. Now, we know that's too many significant figures. We can have 3. So our delta x is 262. I should probably write miles because m might look like meters. So here we go. Let me just draw this so we know it's a significant figure problem. All right, so what do we have now? Well, we know that the first leg of the journey resulted in a displacement of 449 miles at an angle of 65 degrees. And we know the second leg resulted in a displacement of 262 miles at an angle of 335 degrees. So how do we find the total displacement? This is all what we did in Module 3. So I'm going to go ahead and start writing it all down, and I'll start the video after it's done. So let's just take a look at breaking up A, the first leg of the journey, into its x and y components, B, and then C, which is the final displacement. We added AX plus BX, and CY we added AY plus BY. So none of that should be new. So now we can determine the magnitude and the direction of the final displacement vector. And again, that's all that we've been doing in Module 3. We know that the magnitude is the square root of CX squared plus CY squared. And then we know the angle is the inverse tangent of CY over CX. So I figured out the magnitude is 5.20 times 10 to the 2 miles. And theta, or the angle, is 34.7 degrees. The only thing we then need to decide is, are we in the right quadrant? So this is a positive value of x, and this is a positive value of y. So we're in this quadrant right here. So we do not have to do anything. So now, based on our rules regarding equation 3.3, this is the angle for the final displacement vector. In the end, then, the airplane's final displacement vector is 5.20 times 10 to the 2 miles at an angle of 34.7 degrees. I'll circle that. On your own, 4.2. A treasure map says that you can reach the treasure on an island by standing at a certain tree and traveling with a velocity of 1.5 meters per second at an angle of 192 degrees for 45 minutes. It then tells you to turn to a heading of 45 degrees and travel with the same speed for 12 minutes. What is the final displacement of the treasure relative to the tree? The first thing to do here is to picture what's going on. I already drew the first leg in red. So we were going 1.5 meters per second at an angle of 192 degrees. So this angle is 192 degrees for 45 minutes. And then I drew the imaginary parallel x-axis and the imaginary parallel y-axis so that we could do 45 degrees for the second leg of the trip. So that would be right about here. So let's just say that would be something like this. I'm gonna make the second leg in the trip blue. All right, so now ultimately what we're trying to find out, once again, the reason for doing this is what is the final displacement of the treasure relative to the starting point or relative to the tree. So this in green is what we're trying to solve for. We can solve this problem just like we solved the previous one. The first thing we have to do is always list what's given. So we have our velocity in the first leg as 1.5 meters per second. So we know if it's a constant velocity, acceleration is 0. Our time is 45 minutes, sorry about that. So 45 minutes, we should realize right here, we have differing units. We have seconds and minutes. So we have to convert everything to seconds. So 1 minute is 60 seconds. So if we get our calculator, we can say 45 times 60 is 2,700 seconds. That's too many significant figures. So we can only have 2 right here. So which also equals 2.7 times 10 to the 123 seconds. All right. Then we have to once again remember our one-dimensional motion equations, and we know that there's a constant acceleration with 0, and it is for linear motion. So using these equations, we're going to use our displacement one. So delta x equals the velocity times time plus 1/2 a t squared. Once again, this is 0. Anything times 0 is 0. So our displacement equals 1.5 meters per second times 2.7 times 10 to the 3rd seconds. Seconds cancel out, so we're left with, let's get our calculator. We have 1.5 times 2700. We get 4,050 meters. We know that's too many significant figures. So we have to round that to 2, and we get delta x equals 4.1 times 10 to the 3rd meters. So for the first leg of our treasure hunt, our displacement is 4.1 times 10 to the 3rd meters. So now we have to do the same thing for the second leg of the journey. So let's figure out what that is. It can, okay, it then tells you to turn to a heading of 45 degrees and travel with the same speed for 12 minutes. So our velocity is the same, 1.5 meters per second. Our acceleration still 0. Our time is 12 minutes. Once again, we should realize minutes and seconds we have to convert. Okay, and the minutes will cancel out. Let's get our calculator and say 12 times 60 equals 720 seconds. We can only have two significant figures, so that equals 7.2 times 10 to the 2 seconds. All right, then we have to use our displacement formula equation to figure out what that displacement is. So delta x equals v naught times time plus 1/2 at squared. Again, this is 0. Anything times 0 is 0. So we're left with delta x equals 1.5 meters per second times 7.2 times 10 to the squared seconds. Our answer is going to be in meters, which it should be because it is a displacement, which is a distance. 1.5 times 720. We get 1,080. Meters. Again, that's too many significant figures. So that is 1.1 times 10, 1, 2, 3 to the third meters. So just like we did in problem 4.1 now, we can add the two displacements in order to get the final displacement. So we have the displacement for the first leg. We have the displacement for the second leg. Now, because we've broken these up, we can recombine them and figure out what the displacement is for the final. So I'm going to turn this off and then write it all down for you. To add these two displacements, we must first break the vectors down into their components to make the notation easier. So let's call the displacement vector resulting from the first leg of the journey A. We will therefore call the second vector B, and the final displacement vector will be known as C. Now that we have the final displacement broken into its x and its y component, we can figure out the magnitude and the direction. So let's get started on that. So we did the problem, we solved it and got theta is 1 degree. We have to be careful of our significant figures because there's only one significant figure in here, so we can only have one. So we have theta as 1 degrees. However, are we finished? Our CY component in this problem, if we go back, CX is negative and CY is negative. So which quadrant are we in if we draw that? Negative x is here, negative y is here. So we are here and here. So this is where we are. We have to add 180 degrees. So our final answer, the treasure's displacement vector is 3.2 times 10 to the third meters at an angle of 181 degrees.